All right, welcome to the last unit of Chemistry 1. Unit 4, we'll be starting with Lecture 34. This is Chapter 8, Section 1. Now, Chapter 8 deals with more complex, more complete versions of bonding theories. You see, VSEPR, VSEPR, valence shell electron pair repulsion, that's incomplete. It explains geometry, but it doesn't explain why bonds form. Okay? So geometry, yes. Why, no. So an attempt to make up that deficit is what we get here in Section 1 with valence bond theory. Okay? It is trying to explain the why. Why do bonds form? And what it says is fairly simple. Bonds form when atomic orbitals overlap. Okay? They overlap, they mix. This allows their electrons to come together and form a happy bonded pair. Okay? So you'll often see a graph that looks somewhat like this. Here you have energy, and this is internuclear distance. That is to say, how far apart the nuclei are. Okay, so you have a zero energy here, just to say they're distant enough that there's no significant interaction between the atomic orbitals. So you bring them in from, an increasing distance, energy starting at zero. As they get closer, the orbitals start to overlap, and you get this minimum down here. The minimum is when you're at the bond distance. Okay, so this is, no interaction. What's happening over here on the left, this shoot up to infinity, is when, the atoms are getting so close together that nuclei are, bouncing off each other, basically. The positive charges. You're starting to get lots and lots of repulsion. It's not just the nuclei, but electrons too. Remember, you have a lot of full orbitals down inside the core, right? So down here at the minimum is where you have the happiest mixing of your orbitals. Whereas out here at a distance, there's just no mixing. Okay? And here, lots and lots of mixing. Too much mixing. Okay? So that's valence bond theory in a nutshell. Okay? Bonds form when orbitals overlap. They are happier when they are overlapping. And more overlap is better. So what this graph over here on the right is telling us is that you're striking a balance between the happiness caused by overlap versus the sadness caused by getting the nuclei too close together. So the best sorts of overlap, okay, so great overlap is between two s orbitals, or an s and a p, sub x, or p sub x and p sub x. Whereas merely okay overlap is p sub y and p sub y versus p sub z and p sub z. Now, where the heck did this x, y, and z come from? What am I talking about here? Remember, there are three p orbitals. Okay, there's one pointing up and down, there's one pointing left and right, and there's one pointing in and out of the screen. Okay, that looks awful. So let's try to give it more of an angle. There we go. So one in and out. Okay. So, I don't know, let's call this p sub y, p sub x, and p sub z. The reason I chose p sub x for the one in the middle, you'll see in a second. Okay, so X, Y, and Z just mean that they're pointing in the three different directions, like the three different axes on a three-dimensional graph, X, Y, and Z. So that's where those names come from. Now, why do we get great overlap with some p orbitals, whereas, the other p orbitals only give okay overlap? Well, that's just because here we have, nucleus A. Here we have nucleus B. We draw a line between them. Okay, and this is the x-axis. Okay, so you have a px orbital here, and you have a px orbital here. You see, hopefully, that when you bring these two closer together, you're going to get a heck of a lot of overlap. So this is px and px. Whereas, you have one pointing up and down, one pointing up and down. You just can't get that overlap when you bring them closer together, not in the same way. Okay. It is sort of possible to, sort of smear the y orbitals a bit to get some overlap. Okay, but it's different. It's not as good. Okay, so this is what we're talking about in bond theory. Okay, so one of your p orbitals is going to be great for overlap. The other two are only going to be okay. Now the s orbital, it's always good for overlap because it's uniformly symmetric. It's spherically symmetric. It goes outward in all directions. So what this is telling us is that, s orbitals are always able to overlap. P orbital only gets great overlap if it's, end to end or along the line in between the two nuclei. Okay? Whereas the okay overlap, the only okay overlap, that is when, if this is the line between them, then they are only okay when they're perpendicular to that line, pointing up and down or back and forth, but not along the line. Okay, so that's what px means in this case. It's pointing along the line. Y and Z are not. So we have two kinds of bonds, okay? The great overlap and the okay overlap. And we have different names for those, okay? First up, we have sigma, and the other one is pi. Okay, these are Greek letters. So sigma, sigma, and pi. Okay, this is the Greek letter S, okay, and this is the Greek letter P. Okay, I mean, letters have names in non-English languages, or, well, non-Western European languages. Like in Hebrew, it's Aleph, Beth, Gimel. In Greek, it's Alpha, Beta, Gamma, and so on. And the sound of the letter is represented by, just the first letter in the letter. That's because once upon a time, they weren't really letters, they were words, and the symbol was actually a picture for the thing. Anyway, so we have sigma bonds and we have pi bonds. Sigma bonds are, S and S, or PX and PX, or S and PX. Pi bonds are when you get PY, PY, or PZ and PZ. You cannot get, just FYI, you cannot get PYPZ or PXPZ or PXPY. Okay, that just doesn't work. Not in valence bond theory. So sigma bonds are our great overlap. Pi bonds are the okay overlap. Sigma bonds are along the line. Pi bonds are parallel to the line. So that might be a way to remember it. Pi, parallel. Parallel for pi. Sigma are super along the line. I always try, I usually fail to come up with good mnemonics for these things. So, let's look at single bonds, double bonds, and triple bonds. A single bond is equal to 1 sigma bond. A double bond is 1 sigma bond plus 1 pi bond. And a triple bond is a sigma bond and 2 pi bonds. Okay? So the first bond between any two atoms is always going to be a sigma. Okay? The additional bonds formed after that for multiple bonds, those are going to be pi bonds. Now, why these are called sigma and pi and where these came from, they're not actually original to valence bond theory, but this is a good place to introduce them because it's a great way to sort of help understand this concept. So let's go ahead and see if we can't draw some of these bonds. So let's look at hydrogen molecule. Now the only doohickeys, the only orbitals available to these guys are the 1s orbitals. Okay, so we have a 1s orbital on this hydrogen, so that's a sphere, and a 1s orbital on this hydrogen, another sphere. So you bring them closer together, and what you're going to get is something like this. Okay, 2 orbitals overlapping, and that's a sigma bond. Okay. For others, it gets a little bit more complicated just because there's more orbitals flying around. So let's abstract it a bit, not necessarily look at particular molecules. Let's look at px plus px. Okay, so here you have the 2 p orbitals. Okay, and so you bring molecules closer together, or you bring atoms closer together so they can form bonds, and you get just a heck of a lot of overlap between your px and px orbitals. So this is another sigma bond. And then you can also get an s and a px. And just to draw them overlapping really quickly. Okay, so this is yet another sigma bond. So those are the 3 sigma bonds: S and S, S and P, P and P, okay, PX and PX. And the 2 kinds of pi bonds, okay, well, just also to stress, okay, sigma bonds always form along the line between the nuclei. Okay, so, if you have, your 2 atoms, okay, for your sigma bond, the sigma bond is always going to fully occupy the space in between the 2 atoms. That's where the electrons live. Okay. And that's not true for pi bonds. Okay, so for our pi bonds, okay, I'm only going to draw py plus py because PZ goes in and out, and that gets a little bit messy. But it's exactly the same, just, rotated 90 degrees. So you have py and py, okay, and you bring them, closer together so that they can mix. Okay, so here's your molecular center, or your atomic nuclei. Okay. Okay, you bring them together so they can mix. They're coming closer together. And here's, your nuclei. And what you get is something more like this. Okay, so the orbitals have overlapped. Okay, they sort of had to bend to do it. Okay, and you get these regions on either side. Okay, so this is the interatomic axis, that X line. And this is, the py orbitals, mixing together. So the electrons, instead of living in between the atoms, they live above and below that line. Okay, And for the z orbitals, if you can imagine these lying in and out, okay, you're going to get the same thing. Here's the line in between, and the electrons live off of that line. Okay, so notice, like resonance, they live above and below simultaneously, or in front and behind simultaneously. Okay, but pi bonds are off the line. Okay, they are parallel to that line. That's going to be a big deal a little bit later. For this section, for Chapter 8, Section 1, we're just focusing on those facts. Sigmas are on the line, pi are parallel to the line. Okay, they are off the line. Okay, above and below, or in front and behind. So above and below, or in front and behind. That is a terrible ampersand. There we go. Now I see what happened. Okay, so those are sigma bonds and pi bonds. So real quick, let's identify some bonds in various molecules. Okay, we'll start with methane, or CH4. Okay, so we can go ahead and just draw the Lewis structure really quick. Okay, so carbon down to 4 hydrogens. That uses up all 8 of its molecules, and that's where it lives. So remember, pi bonds are only if you have multiple bonds. So this right here, the first bond between carbon and hydrogen, okay, that's a sigma bond. This is a sigma bond. This is a sigma bond. And this is a sigma bond. So all of the bonds in methane are sigma bonds. Okay, they're all single bonds, so they're all sigma. Oh, so that's another way. Single equals sigma. Okay, sigma equals single. Okay. Okay, so that works. The first bond, a single bond. Okay. A single bond is simply sigma. Ooh, that's good. Alliteration for the win. Okay. So now let's look at ethane. Okay, the next smallest molecule, so C2H6. That is like if you attach 2 methane molecules together. Okay. So now what we see here is we see a whole bunch of single bonds. So these are all sigma. So 1, 2, 3, 4, 5, 6, 7. So we have 7 sigma bonds. Okay. So every single bond there inside of ethane is a sigma bond. Now let's do ethene. Okay, that's C2H4, or swamp gas. What we've done there is we popped off a pair of hydrogens so we could make a double bond between the carbons. And we'll go ahead and we'll draw with the appropriate geometry. You know that this guy right here, he sees this carbon on the right has 3 electron domains, so he has a trigonal planar geometry, and this carbon over here likewise 3 electron domains, so a trigonal planar geometry. So the carbon-hydrogen bonds are sigmas. That's true on both sides. Okay. But this bond in the middle, that double bond, is 1 sigma and 1 pi. Okay, so a sigma bond and a pi bond. So if you were to look at this molecule, sort of edge on, okay, so there's carbon, you would see, a sigma bond in between the 2 carbons. Trying to draw it, so you're looking at it from the side. I've rotated it. And then you would see above and below, that pi bond. Okay, so the first bond is right there. That's your sigma. And these 2 here are the pi. Remember, every pi lives above and below, or in front and behind, both at the same time. All right. Next up, let's do a quick survey of ethine, aka acetylene. Okay, so if you've ever done any sort of welding, some of you might have, I don't know, then you'll have worked with this. It's C2H2. We've removed another pair of hydrogens in order to make a triple bond between our carbons. Okay, so this here on the left is a sigma bond. Over here on the right, we have another sigma bond. In the middle, we have a triple bond, so it is a sigma and 2 pi bonds. Okay, so now we have C, let's C and H. So the first bond lives directly between the two carbons. That's our sigma bond. Then we have another bond that lives above and below. That's our first pi bond. Let's go ahead and call that pi y. And then this one will be a bit harder. So let's go ahead and maybe draw it a different color. Ooh, that's not working. Let's, okay. So I immediately rue and lament this. Okay, so now in front and behind we have pi z. Okay, so those are the 3 bonds of our acetylene. So 1 sigma and 2 bonds, 2 pi. So above, below, this is what I'm trying to draw here, in front and behind. Okay, I'm trying to draw 3 dimensions. It's not necessarily the easiest thing in the world. Sorry about that. And finally, one last molecule. Let's go ahead and look at formaldehyde. Okay. CH2O. Okay. So that is a carbon singly bound to hydrogens, bound to an oxygen with a pair, 2 non-bonding pairs. Okay. So this carbon looks around itself, sees 3 electron domains. This oxygen likewise looks around itself, sees 3 electron domains. So that means that we have a sigma, and then this double bond is sigma plus pi. Okay, it's a sigma bond and a pi bond. All right, so that is formaldehyde. A sigma bond between each of the hydrogens and carbon, and then between carbon and oxygen, a double bond composed of a sigma bond and a pi bond. Okay. All right, and that is all we're going to cover for valence bond theory. See you in lecture 35 with chapter 8, section 2.